Welcome to Ask and Learn.
This problem is a little bit of a generalization of the previous problem, where we now have kind of two disks connected together, and the smaller one is rolling on a surface without slipping, and the larger one hangs below the surface. So again, obviously this would look something like this. The surface is here, and then something is hanging below it. I'm not sure exactly what that would be, but and then we have a spring up here, and again, in this case, it actually looks like it's wrapped around this larger diameter here. And again, it doesn't really matter whether it's pinned to a point on the diameter or it's wrapped around. If we're only considering small rotations or small motions of this system back and forth. So we can let's see here. We can look at the potential energy, so that's 1/2 k times the change in length of the spring squared. And the change in length of the spring is this distance here. So this distance to here, which is the little radius, plus this distance here, which is the big radius. So that's little r plus big R squared times theta squared. Now we're told we're given the moment of inertia about the center of mass of this thing in terms of a radius of gyration. So we have the rotational energy about the center of mass and plus the translational energy of the center of mass. Because it's slipping at this point here, the translational velocity is r theta dot. So in the end we get T equals 1/2 kcm squared plus little r squared times theta dot squared. Now we can again pick out our stiffness. Equivalent stiffness is just this term here. So that's k times r little r plus big R squared. And our equivalent mass is this term here. And so we have that. Now we can, we basically just define this as KEQ and this as MEQ. So then when we take the total energy and take the time derivative, we get theta dot all times MEQ theta double dot plus KEQ theta equals 0. And again, since this must be true for all time, this must be 0 for all time, or this must be 0 for all time. Well, that's the case where it's just static, so we're not interested in that. So we're interested in this case. So this must be 0. We can divide through by MEQ, and then that becomes theta double dot plus omega n squared theta equals 0. And omega n squared, omega n equals KEQ squared of KEQ over MEQ. We know what these two things are. We have values for all of the terms in this expression, and I guess I forgot to write. Let's see here. I forgot to write down what kcm was. That is 0.125 meters. So we can plug all our values in, and we get that the natural frequency squared is 468 radians squared per second squared, so our differential equation becomes theta double dot plus 468 theta equals 0. And that is the differential equation that governs the motion of this thing back and forth.